This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Is it? All right. It's even nicer. Okay. Of course, this now the touch panel is not working. Oof, it's every time, man. All right, thank you.
Yep.
Okay, we should start. It's loud enough. Good. Welcome, everyone. Tomorrow is the mid-semester test. It's going to be somewhere else. You know where it is, right? In LMS, I put the map. So we will do it there for 1 hour. Don't forget to bring your handwritten cheat sheet or notes, 1 page. Yeah, or read the LMS for instructions, please. And if you still have questions, of course, still ask. And if it's not handwritten, yeah, I will be taking it away, right? So that's the. There is great benefit in preparing your handwritten 1 sheet of notes, and then in the final it will be 2 sheets of notes. So it's not about memorizing stuff. When you write it down, you will learn a lot by just writing it down yourself. All right, and then as I said, maybe I haven't emphasized enough. So it will be only questions about the basics, fundamentals. So don't if you know the fundamentals and you have put effort to the subject, it should be fine, I believe. We'll see tomorrow together, or I'll see afterwards while marking. Yeah, usually what happens with these subjects is 1/3 of the people are here. They will be in good shape getting some H's. Then there is another 1/3 who cannot come for various reasons, but they diligently watch things and keep track. They're also in good shape. And there is 1/3 who neither comes nor watches anything and then tries to study 2 weeks before the exam, final exam. Some portion of them get away with it and we kick them to cross the boundary. They get a P. And then some portion cannot keep up and then fail. And then when they fail. I honestly don't feel too bad when I see an empty exam sheet, because how can I give partial credits when the answers are empty, right? So that's the story with everybody is focused too much on the final and so on, so I want to get it out of the way. Actually, we are starting now no workshops this week. I have announced it on Monday, except from Friday, because the next week's Friday is the official holiday, Good Friday, and then those people in that workshop miss it simply, and there is no provision to making it up. Therefore, there will be a Friday workshop this week. I thought it's not a problem because it's after the mid-semester test. So Sergey will hold the Friday workshop this week, but all other workshops are off. Any questions or concerns before we start the fun part of the subject? So all the material we have done on optimization, as you have noticed in workshop, is used heavily in engineering applications. Right? I gave examples from power systems, communication networks, and so on. So that is well known, as I was saying in the introductory lectures. But they are also built into, as you will see, to machine learning. Machine learning makes heavy use of optimization. So most of it is actually optimization. So plus some probability. We were talking about, just to refresh the memory, we were talking about linear regression, which is kind of very, very fundamental 101 of when people talk about machine learning, is curve fitting. Another name for it is curve fitting. So you are given a set of data points, like these blue ones, that are generated that come from something, right? In this case, we know where it's come from. Normally, you don't know what generates the data. If it's a natural process, it's not easy to figure it out. In this case, it's very simple. Some sign plus noise creates these blue points. The green curve is the sign that generates these noisy blue points. So that's the ground truth. And then, we say we have an oracle telling us where the data comes from, but in reality, you don't have an oracle. And the goal is, can I fit a polynomial here, model this data? And then if I fit a polynomial, with my criterion is minimizing the mean square error or square error, some square error, it's just all the same story. And then if I have such a model, that's good, because if in the future data points I can predict, I can make prediction, I can describe it, and so on. So the model is a linear model, linear in some basis functions. The basis functions are multiplied with these W parameters. The basis functions are functions of X data, but the basis functions do not have to be themselves linear, and they are not. For example, if I I can choose the phi as 1x, x squared, x cubed, right? That's not linear in X, the individual components, but then the W's that multiply them, and this whole dot product between phi and W and V, that's a linear operation, the dot product. And the error is, as I said, the error between what I observed, the y's of corresponding to the x's, and then what my model tells me. And that's what I use to determine these weights, the v's. So this is actually, it's a quadratic cost, and I'm trying to minimize this quadratic cost or error, and that's a simple optimization problem. It's an unconstrained optimization problem. I haven't put any constraints on the v's. So you can take the derivative, and and then if this is invertible, you get some set of equations. You can use different methods to solve for this set of equations here for v, and get the weights. One of them is matrix inversion if the matrix is invertible, but even if it's not invertible, you can do pseudo inverse, and there are a lot of methods to get the v's, right? So that's how linear regression works. And then we did some simple question where we had a linear model where the basis functions were sigmoids, and we have shown that the sigmoids are closely related to hyperbolic tangent function. So this was just an exercise in little bit of mathematics, but also introducing the sigmoid, which we will encounter again. And I think I stopped there. And then the interesting question here is, I mentioned this, there's this, in the polynomial approximation, you can do cubic, you can do you can include x to the 4s, x to the 5s, x to the 6s. Your model, of course, gets more and more complicated, right? If it's a higher degree polynomial, that's a more and more complicated model. You have to decide an increasing number of parameters and how to find them. Of course, they will come from this optimization process of minimizing the error and solving the corresponding set of equations from the first order necessary and sufficient conditions. Well, but then you still need to decide on this model degree, function degree m. So in this case, specifically, this is an example, which model to choose. Here we are talking about, this is a general question. So these questions are actually very general, applicable to many, many machine learning algorithms. I'm just illustrating them within this specific context of polynomial curve fitting. Right? What model to choose is you will encounter often here. The model is polynomial function. Let's say I make that decision. What are the model meta-parameters? In this case, the meta-parameter is the polynomial function's degree. There may be multiple meta-parameters. It could be the parameters of the basis functions that you have chosen. If you have chosen a sigmoid, then there are additional, the basis functions have these meta-parameters in addition to degree. Then, which evaluation criterion am I going to choose? Here, the sum of square errors. So this is visually really nice. Green is the ground truth, which is often unknown, as I said, but in this case, the oracle told us, oh, I generated these blue points using a sinusoid plus error, right? So that's good. You know what this oracle thing is? Like I keep saying, but you know, in ancient Greek mythology, there is that oracle that tells you the future and so on, right? That comes from Greek mythology. If I find the opportunity, I can use also Norse mythology, which is nice, but I couldn't find anything about Odin or Thor to plug it in. Next time, maybe. And then those are the only ones that I know, sorry. There must be others. So if I use a m equals 0, it's a constant. Obviously, that's not a good model to describe these data points for this case. So you see the blue points and then the red curve. Curve is just a constant. You know, it's not that good. M equals 1, maybe not that bad if you ignore this much noise, right? M equals 3, you know, things are looking better here, you see? The red curve explains the blue dots to some nice extent. How about M equals 9? I have removed all the error, but, you know, my model is pretty complicated, right? So, is this the best choice? Or why not? That's a deep question. And this is very much the definition of overfitting. So you are overfitting to the data. You're being too good of a student. And you know, while trying to study for H1, you miss the big point. You know, students do that. Actually, that's a good analogy. You know, sometimes students are too good students. They trust the system too much. And they think, if I get 100, I have taken everything there is to take from the subject. It's usually the opposite. Usually, to get 100, you focus on the wrong things. I'm also suspicious of students who get all 100s. Either the student is a genius, it's very trivial for him to get 100, or her, or the student doesn't have a judgment and studies just to get the 100, not the main thing. The main thing is explaining these data points, not getting 100. Minimizing the error to 0 is not the main point. And that is the overfitting. What happens when the model matches too closely or exactly to the particular set of data and therefore fails to fit additional data that comes afterwards and predict future observations reliably? You know, when you overfit the future data points, you may start to make big errors there. So there are two conflicting goals to trade here. Represent the training data that you have well, good, but also perform well with the future new data. So that's the concept of generalization, right? Here visually, classification example, if you draw the green line as your boundary, maybe you are minimizing the current error, but then you may do pretty bad with future data points because the underlying model maybe is much simpler, this smoother curve. Or regression example, this blue curve is clearly overfitting, whereas even the first order model is pretty okay. There is this underlying assumption here. One has to be careful about it. The underlying assumption here is the generator process is rather simple. So we make a choice for simpler explanations over more complicated explanations. So, and we assume that the underlying process is simpler in general than complicated. So that is philosophically Occam's razor, right? So this goes to Middle Ages. Some guy, Occam, said, this is the rephrased version. He said it in a very complicated way. When presented with competing hypotheses, like models, as we were saying, like these are competing models, different M's end up with different polynomials as the models. To solve a problem, one should select the solution with the fewest assumptions or fewest parameters, right? So we tend to choose the simpler explanation whenever possible. But, as also Einstein has said more recently, everything should be kept as simple as possible, but not simpler. You also see that in the previous slide, right? As simple as possible, but not simpler, right? You can also oversimplify and miss the point. So I'll come back to this. So as I was saying, we are assuming a prior that the processes have often a simpler explanation, and we try to choose the models that support that simpler one. Of course, if necessary, we make them more complicated, as supported by the data. There is a practical way of doing it, and that goes back to the training set, test set, or cross-validation, actually. And this is a very great, there is a very good discussion in Bishop here on this topic, and I just took it wholesale from there. So we can use the square error to choose M, and you know, if we do a lot of computational work. So if you take the data and then, as you should, divide it into training test and test set, right? Then the error, the blue one, you can actually, by choosing a more complicated model, M is your model complexity in this case, the degree of your polynomial, right? You're following up, right? Everyone is with me. This is kind of important, very important. So as M increases, you know, my training error will, as you expect, will go to all the way to 0. With M equals 9, I'm hitting all the training points, you know, error goes to 0. But what happens with my training set is much more important, right? Because training set is the new data that I haven't seen. The test set is the... So what happens with my test set is the important thing, not the training set. The test set represents the data not seen in the training set. And with the test set, you know, as I increase the model complexity, up to a point, things start to get okay. M increases, you know, it doesn't change much. This is just a specific example, but you see, if I start to overfit, suddenly it jumps up, right? All the way. So training, in this case, I increase the model complexity, but I'm deceiving myself because on my test set, it doesn't work. And if it doesn't work on my test set, I have failed. Right? And you can do this with the cross-validation as well. The only problem is this takes a lot of work, right? You need to try all the models and then do this whole full testing. And if you have the computational effort, you can do this. Otherwise, you need to use, maybe you can only do this part or use a little bit of judgment instead. It is also visible in terms of how the parameters look like. Well, when M equals 0, here you see omega 0 star is the optimal one that fits. M equals 1, I have a refined model. M equals 6 is a 6-degree polynomial. Yeah, there's a typo here. You're right. It should be M equals 3. I don't know why. Yeah, I took the table. That seems to be a typo. Very good. And M equals 9. Also, you see the numbers. They get crazy. I get a very high numbers as parameters. That also tells me this is a very complex model, and maybe I'm going against Occam's razor here by seeing these very high numbers. Yes.
Is it a coincidence that you kind of pick the polynomials?
It's all coincidence. Yeah, coincidence. There's you can choose M1 to 0. You can do all the 9 and 10 and 11. Yeah. No, it's just pure coincidence, and there's a typo here. I didn't notice. So why? So this quantifies nicely why M is 9 is oversitting, right? So MSE in the test set and parameter values of the model both increase. Mean square error increases, parameter values increase, and then less performance with new data, and also violating Occam's razor because we are getting these parameters that are very complicated. We get a complicated model to explain the training data. All right, so this is a really nice example. So then this is to illustrate it. How am I going to fight against it, right? So I don't want this, so how can I prevent it? One way of addressing overfitting is obtaining more data. Like, I mean, if you have this data set, maybe 15 points, and then you may get this with polynomial M equals 9. Let's fix the polynomial to 9, 9th-degree polynomial, and see how it performs with 15 points. Then you get this red curve here, 15 points. What if we give 100 points? Remember, the 100 points are generated by the sign plus noise, right? So we have actually a simple process behind the scenes. So, and if you have a lot of data like this, the same 9th-degree polynomial actually becomes pretty nice. So even the 9th, if you are not overfitting, so for a given model complexity, in this case a high M, the overfitting problem becomes less severe as the size of the data set increases. So that's good. The issue is, in real life, you may not have too much data. Then either you're going to go either you're going to have to work with less data, whatever you have in hand, or you need to take the data set and create synthetic data, but that's also a bit half cheating. You know, train a model, generative model, and then extend your data set artificially with the things that you have yourself generated, and then you're not cross-checking anything because you have no chance. So it's a bit of a rabbit hole that can be done, and there's literature on that too. So, but yeah, that's one pathway. The other thing that is maybe more elegant is put restrictions on model parameters. So I should penalize maybe the model complexity, which I'm not doing in the mean square error, right? Mean square error is only about the error, how well I'm fitting to my model to the training set. So, but if I put but I have another objective in mind, right? Now that you know optimization, right? We were talking about this. So we have one objective that is mathematically expressed in the objective function, error, square error, but the second objective of simplicity I haven't expressed in the objective function of the mathematical, you know, optimization. Therefore, the optimization doesn't know what I want, and if I don't express it, it will always solve it, you know, only according to one objective. So we can actually add this additional objective, and that is what's being done with regularization. Another option is decrease the number of the model parameters. Essentially, that is decreasing the model degree in this case. So I can choose m equals 3, m equals 4. Yeah, that works too, as we have seen. But sometimes it's not that simple. For example, in neural networks, you have a lot of parameters, and then you don't want to decrease their number, but you want to do something else, restrict them in other ways, and that is a regularization. Right? Is it all clear? Do you know this stuff or no? But it is important, so now you are learning. As I am saying, this stuff will pop up in everything, in classification, in neural networks, you know, in everything. I'm just illustrating it using the regression, because regression is easy to understand, curve fitting is very intuitive. So the idea is add a regularization term to the error objective. Now you see, I was talking about the multi-objective optimization, right? What do you do when you have multi-objective optimization? You either put the two objectives and put a weighting factor between them, or you put the, you know, one objective to the objective function, other objective to the constraint, so that you guarantee some minimum performance in terms of the other objective, right? But in this case, we do the simplest thing that you can think of, put both of them to the objective function of the optimizer and put a weighting term to shift the weight, you know, between one objective to the other. If lambda is 0, then we are back to just focusing on the error. And if lambda is infinite, very large, then error is not emphasized, but everything is about the second term that I have included, right? So lambda is my sliding, slider. Yeah, that you know, go from one to the other. So you find the weight, the balance between the two objectives. It's a weighted, weighted sum method. So this is data-dependent error, and this is the regularization term, and lambda is the regularization coefficient. Official names, these are well-known terms. Everybody calls them the same thing, so it's good to know. All right, and how does the error term look like? This is t is the label. So we have xt. It was xy, now it's xt. Doesn't matter. So my model's output, model takes x, gives t, and then the real t in the training data. The error should be minimized. Error is mean square error or some square error. And then this is the regularization term, which is a quadratic cost on the parameters, right? So we will come to this, why we are using the quadratic cost and other ways of doing it. So this is also known as ridge regression or penalized least square, as appropriately named. You know, when you go to sklearn, it's ridge regression. So the total error function is this, and if you solve for this, you know, we are solving this with respect to w or v, and then it's an unconstrained optimization problem, convex, has a unique global solution, and global solution, you can write the first order necessary conditions, and then if this matrix is invertible, which will be because of the lambda I is the diagonal matrix, so it's lambda 1 or lambdas all diagonals, and then that will make it invertible in many cases. Then this can be inverted and then find the solution as before. Or you write the first order conditions as set of equations and solve for them and get it, or you give it to a solver to find the best solutions, right? So here are some links to the articles that are okay. So there is no big difference in terms of what we had before. So the solution was this. The difference here is, you see, this was the term. Now the term has the matrix inversion has this diagonal lambdas. So if the lambda gets large and large, W's are suppressed. They become smaller and smaller. So we kind of prevent also these crazy W values or omega values. A more general formulation than this is this, like this. So we have a absolute value and then to the Q, where Q can be different. So if Q equals 2, then we have the quadratic regularizer as before. But we can also take Q as 1, so then that would be the L1 norm, right? Or Q can be also larger. So if Q equals 1, that's the L1 norm. And that is a specific case. It imposes some sparsity for large lambda. If I choose a large lambda here, putting a cost on the absolute values of the parameters ensures that some of the parameters, we force some of the parameters to be very small or zero them out. And if many of your parameters zero out, then that's called by definition sparsity, right? So if you may have a 10th degree polynomial, but what if they are W2, 3, 5, 7, some of them are zero, then you have a sparse polynomial, less terms, and we have achieved some type of simplicity again, preventing overfitting. So there is this visual way of interpreting it, kind of just for intuition. So L1 norm will look like this, this cost. L2 norm is looking like a circle as usual, and then if you make the Q equals 4, then it starts to look more and more like a square maybe, and then this looks, with Q equals 1, it looks like a diamond. And then when you solve this multi-objective, it is a bit like having a line and then touching this additional function, and if you see this line either touches here, which zeroes one of them out, or here, which zeroes the other one out. Whereas in the quadratic, you get both of them some number, but maybe smaller. And then it is less and less so when you go to Q higher, still has an effect. So sparsity is also desirable computationally, because if you have less parameters, then you do less operations after you train your model. And then finding running the model is cheaper, and also it's appealing from, as I was saying, Occam's razor's perspective. So you end up with it's simpler model because some of the model parameters are zeroed out, right? So in this case, the polynomial is maybe higher degree, but it's simpler because many of its components have a zero parameter. All right, so actually all this stuff is part of your one-to-one part of your workshop too. You will see it all there, or maybe you have already started. How many people started? Not many. So it is due after the teaching break, so you will have enough time, yeah, for the workshop to play with it. And yeah, all this stuff, as I was saying, trying different regularization, how the regularization affects things. I've given you this toy problem with simple data set where you can actually really see it for yourself and experience for yourself. So, any questions? Let's do a question together, unless you have specific conceptual questions. This will hopefully make it a bit more concrete. We have a linear model of the form, W0 plus sum of Wi xi. This is linear in the terms of the data points, right? And then together with the sum of square error of the form. So this is very much, I'm given a data set x and t's in this case. Sometimes they are called xy's and sometimes xt's. So then output of the model should match the the given ones in the training set. Of course, we are talking about the training process here. In the training set, I should minimize this error. And then the question now says in something interesting, right? This is the non-regularized version. The question says, now suppose that there is a Gaussian noise, epsilon I with zero mean and fixed variance sigma square is added independently to each of the input variables xi. So xi's become noisy versions of xi, just like that sine plus noise thing. And then, of course, if that is the case, this is Gaussian noise is zero mean, then expectation is zero, and then they are independent. Therefore, epsilon I, expected value of epsilon I square is only sigma square when the epsilon I is equal to epsilon j. Otherwise, this product, because they are independent, the product is zero. So this is the Dirac delta function, indicator function, right? And then we make use of that to show that if we minimize this ED averaged over the noise distribution is equivalent to minimizing the sum of square error with an additional regularization term in which the bias parameter is omitted. So there is this small thing about the bias parameter, but except from that, it shows that if we minimize the noisy error, then that's equivalent to doing a regularized minimization. So can we show that? So we will try to do that together. So I was talking to a friend, and then I was telling him, how I run this course, and said, I'm solving examples during the subject, and we said, that's a good thing. Most people also say it's a good thing, solving examples rather than just going through the slides. But then he was saying, do you give them opportunity to solve it themselves first? And I said, no, I was just solving myself. So then he said, maybe it would be better if you just give them an opportunity to solve it. And that's what we're going to do now. You have 1 minute to start, giving a shot, and then you can guide me in solving, and then we can still do it together. So you can work with your friend next to you and, have it a go, and then give me some guideline how we should do it. Actually, I can give you an initial kick with the what we have here. So we have the y here. That's good. What is meant here is, so that we are all on the same page, we have a y tilde now, which is w0 plus I equals 1 to d, and wi, or omega I. But now my x's are noisy, so actually xi has an epsilon I, where epsilon is this Gaussian distribution, zero mean and fixed variance. So from this point on, maybe you can start somewhere. I also give one more hint. So we can define also the error now with the noisy version. So this tilde version. And it will be, so now the sum is over all the n. And then y tilde I minus, or we can do n here. Let's be consistent. So we have the data set is or n. Don't sleep. Okay. Has anyone progressed? Maybe someone can guide me. What do? We should choose someone to tell me. I need a victim. Or the opposite, a hero.
Substitute yx.
Yep.
Substitute y into the
Yep, we substitute y.
sum of zero.
All right. So could you walk me through? Then I don't make much typos either. That's better for me. So I have the sum over n, and I substitute y tilde into it. So when I do that, what do I get? So actually this is, nobody told me, right? This is square. Well, you were supposed to tell me that as well, right? So it was a square error. What happened to that? It's here. So when we do the square, first let's write it y tilde n square minus 2 yn tilde tn, right? Plus tn square. All right? Yep. Then, as you say, now I substitute the sum and then what? What do I get if I substitute? Right. So this y tilde, first of all, before I substitute, can I write it in terms of yn? Y tilde equals y. Most of the terms are similar, right, with yn. So y tilde n equals yn plus, what are the differences? Sum over I equals 1 to d. Omega 0 plus omega ixi's are belonging to yn, right? From 3.106 to 105 here, you see? Plus, then I've got the omega i's, epsilon i's. Huh? Is that clear? So we have this from 3.105 and the star equation. Huh? You see that? All of you?
I think what we can do is we use yn hat. Not do things like the first thing, do like reduce yn hat equal to yn plus the summation of omega I, epsilon I, and normally minus tn. What we want actually is yn minus ti plus summation down.
So essentially we take this and as you were saying, or before was said, we now substitute this into the equation above, right?
Yes.
So if we do that, then help me walking it through. So we have the sum over n. Then what do I have? I need to open a big parenthesis here. So I have now, this needs to be squared, right? So it is yn square plus 2yn and then this sum, right? Plus this sum squared. So that's the first term, minus 2 tn times yn, then minus 2 tn times this second part, right? Which is the sum again. Plus this last term tn square. Right? So you're checking at least, right? So you came this much or maybe not. So what do we see here then? What are we seeing? If we take this, if we take this expectation of error now, we take the expectation of the error, expectation of E tilde. Now this is actually, I should use some script E like this. So expectation of the error, if I take this, then I take the expectation of these epsilons, and I know that their mean is 0, right? So if I do that, the mean, what are the terms that do disappear? So y's are kind of they are non-random terms. Omegas, w's are non-random terms. So a lot of the terms actually disappear. So this expectation of this is 0, right? And expectation of this is 0, right? How about this one? There is a square here. What happens with this one if I take the expectation, expectation of this some square? So that would be then cross terms will be all 0 again because of what the question is saying. So using this, right? So the cross terms 0 out, only the square terms remain, and then they become sigma square. So essentially this becomes omega I square sigma square. That's the variance of the Gaussian. So now I have that because also because expectation of j equals 0. So this cross terms, when you take the square of the sum, they disappear. Therefore, maybe when I write here the expectation of this new error, because it's now a random variable, it's a function of random variables being the Gaussian noise. Noise is added to the individual x's. So I'm looking at what happens in the mean, right? So when I write that down, then what do I get? I get 1/2, and I get the yn square, and then 2 minus 2tn yn plus tn square. But this is the same as 3.106, right? So we should make this note, same as ED, right? In 3.06 above, yeah? But then I have this additional stuff. So plus, I have this new term that should come here. And that is, again, 1/2. Yeah. So it will be then sum of omega I squared this square, right? All right? So then what we have here is basically the previous one. So actually I have space, good. So what we have here is then, as a result, the previous error plus, as we expected, 1/2, and maybe a sigma square I can put it here, and then I can write it also as this form, because that is just the same as the dot product between these two vectors, and that is nothing but wi squared, right? Y equals 1 to d. So that's basically it, right? So we have that. What happened to n? We should have a capital N somewhere, right?
The first sum.
Yeah, the first sum. What happened? That's missing. It, sorry?
You know the outer sum.
Yeah, that should be there, right? Because I have a wrong solution here. Yeah, but that sum is then, because these are the same, it just should come it here as an n, in my opinion. It should be like this. from what I see here. Do you agree?
Yes.
Okay, then the solution is wrong. I need to update the solution. Yeah. Good. All right, because yeah, there is an outer sum here as well, so this should have been here, as you say. There is a sum over n, and this sum was over I. But that sum, there is nothing in here with n, therefore it's just n times something. Yeah, let's write this nicely. All right. N, and then, if I can write, then I will be happier. And this is over I, and this is over I. Yep. Yeah, well, I'm using a bit shorthand, but in the finals and so on, please write it more explicitly. So you should write it a bit more explicitly. Have pity on the markers. It's hard enough to decipher the handwriting sometimes. So be explicit in your writing. Okay, so you see there's this interesting relationship. So if I have a noisy samples, trying to minimize the error of noisy samples is effectively equivalent to having a regularization term, or when I add a regularization term, it is as if I am considering noisy samples with Gaussian noise. So that's that interesting connection going there, kind of, right? It's a nice deep connection. You can interpret regularization in many, many ways. This is one way of to think about it. Math is the same. Interpretation can be done in different ways. I guess it's time to give a break. It's a good point to give a break. And then I will go on with the Bayesian inference. I'm not turn it to a kind of a Bayesian statistics subject, but I would like to cover some of the fundamentals that we are going to use, that is effectively used everywhere in machine learning, so you need to know the basics. The subject is not a statistics subject, but you need to know this much, because statistics is also, just like optimization, pretty much built in to some extent to machine learning and deep learning as well. So if we give a break now, I think 5 past, we can continue. Huh? All right? Excuse me? All the solutions of the... Yeah, of course. I think I'm going to post everything, if I finish it today, or I will post everything this afternoon. I haven't posted them yet. No, they are not there yet. No, I haven't posted them yet. So I will do it. Okay. Oh, okay, yeah. Leaving it on screen now. Yeah, sure, of course. Sorry about that. Yeah, I didn't understand. So you mean leaving it like this? Yep. Yeah, I will post everything as well, but yeah, for now, yeah. So let's give a break, 10-minute break. That should be N. have an n or not? I'm just thinking, does the expectation remove the n? Not really, right?
No, there's no problem.
So n should be there.
It should be there.
Yeah, the solution doesn't have it. That's why, like, this is an error in the solution. I need to update this type solution.
Professor, I have a question. For in the question, we have this, but in the solution, we already set this to be 0.
But, you know, that's the Dirac delta function.
Ah, I see. Okay, thank you.
Yeah, that's a good point. Maybe I should add this. You know, maybe here. Right? So that's a good addition there.
I still don't really understand.
That's the Dirac. You must have seen this indicator function, Dirac function, somewhere. Yep.
I still don't see how you got this one.
Ah, yeah, but that's just you multiply. This is the original definition. When you multiply omega 0 plus omega x I, you just do this. There's nothing going on here.
Why is this
That is why I'm given.
Oh, did I write it wrong?
3.05. That is yn.
Why yn is omega 0?
No, yn is this. Yn is here.
Yeah, and then
That
this,
is omega 0 plus this is yn.
Yeah.
Yeah, yn is this.
Yeah, so that's the original. So this is the
Yeah,
model
so
we're
this is
trying to
yn
make.
plus all the multiplications come here, right?
So yn. So this.
Tilde, that's tilde.
Yeah. So
No,
we're
just
trying to
you're
match
right.
this. We're trying to minimize this error. So this is the model, the output of the model, plus and minus the true data.
Yeah, but now this is the noisy one. It's a noisy
this is
model.
the noisy one.
Yeah. Have a look.
Will you post the answer of the workshop?
No. No way. It took me forever to prepare those. And, if anything, I want to make them a bit more open-ended. But
Yeah, because I feel it's useful to revise.
yeah, but like, no, I'm not gonna post them. Sorry about that. Yeah. If you have anything specific, we can discuss and I can show you. Yeah, you're a PhD student, so we can make exceptions. Yep.
I have a question about this stuff because I couldn't understand why the
Yeah, that's just a graphical representation. That just tries to tell you, it acts like having a line touching this.
A line
So,
touching.
so you know, this line will always touch somewhere in the middle, so they will be both positive. Whereas this will touch, you know, when one of them is 0 or the other one is 0.
Sorry, which one is 0?
And when it touches here, then omega 1 will be 0, and if it touches here, it will be omega 2 0.
Oh, okay.
So you zero out one of them.
Oh, I
So
just
it acts like that. It acts like that. But here, with a quadratic regularization, you most of the time get positive ones. Yeah, because like this point, like their values are positive.
Okay.
Whereas here, one of them is negative, 0.
Sorry, which one is negative?
No, one of them is both of them are positive. One of them is 0. No, nothing is negative.
Oh, I got it. So it's like, so when I try to choose a omega, it should be, if this is 1, it should be 1, 0. If I choose this point.
Yeah.
If I choose this point,
It will be 0, 1.
0, 1. And for this one, I
Will be-
got a sine theta, cosine theta.
There will be some values, right?
Oh, yes. Okay.
But they are not 0.
Yes.
Yeah. That's what it tries to tell you. It's a bit like having a diamond. Like when you have this.
So it's like, should I?
This is actually not the.
Oh, it's not a norm of it.
Yeah, this is not the normed one. Yeah, just
Just the Q.
that's right. But the absolute values of them.
Okay, thank you.
There are different ways of writing it, but yeah. Check the book. There are different ways of. You can also express it in terms of a norm as well.
Yes, thank you.
Yeah. Yeah, everybody's. So. Yeah, I think we can start. I see a lot of people ready for the next round. All right. So, Bayesian, let's do a little bit of probability. So, as I was saying, the optimization plays a huge role in machine learning, but obviously probability plays also a big role. And why? It's not surprising. Why? Because whenever we deal with things that that are uncertain and random, we use the probability mathematical framework of probability to deal with them, right? So this is something you know very well. You cannot tell me, oh, we forgot about it because it was 3 years ago. You cannot tell me that because I know you have taken probability subject last year, at the worst case. So, so it should be even fresher on your mind than linear algebra. But yeah, so that hopefully it won't be a problem. Let's see if we have a joint probability between two random variables and we take the sum, we can find the marginals px or py. If I add over x, I will get py. There is the product rule. That's the key rule that you should know with the conditional probability. Joint probability can be expressed in terms of y given x times p of x, and that actually very much gives us the Bayes theorem, because y given x is essentially from here. Py given x is pxy divided by px, and then I can also use the product rule again, and pxy, the joint probability, I can write it as px given y times p of y, right? So what's the advantage of that? Essentially, you are writing py given x in terms of px given y, right? So you kind of flipped, and this, as you will see, is very useful. It will become apparent. Then this is the continuous version of the sum rule. Sum becomes, in the continuous world, sum is integral, right? And subtraction becomes the derivative. They must have told you that in the calculus. I always feel they make it extremely complicated. All that calculus stuff is nothing but just taking a sum. Integral is just summing up things. So then variance is this, right? So, and then the covariance of two random variables is this. That's also I think that's something you will need also in the workshop, right? With the covariance. Yep. This is the PDF, CDF business, probability distribution function, P of x. And the cumulative distribution function is when you take the integral of it. Of course, it starts from 0 and hits to 1. That's the blue line, and there is a delta x here. Things are easier to deal with when there is a PMF, probability mass function. It's just discrete, and you sum them up to get, again, the cumulative mass function. And then if you take a function of the random variable, then expectation is like this in the discrete case, and then in the continuous case, and the variance of a function of x looks like this. So just to refresh your memories. And then Gaussian distribution is used a lot for multiple reasons. And then this is the Gaussian distribution for a single random variable, and this is the Gaussian distribution for a vector. And nicely, the vectors are here. The vector and the matrix are highlighted as bold. And then this is a multivariate Gaussian, right? With the variance matrix here. And then if the data points are drawn independently from same distribution, they are said to be independent and identically distributed. So if there is a Gaussian distribution, for example, I take x's from the same Gaussian distribution, then we can create a vector out of those x's and make it an x vector, x1 to xn. And then there's that vector, or you can also see it as a set. It doesn't have to be ordered. So it doesn't have to be, if you don't put it to a vector, then it would be a set, right? Then it is IID in terms of its elements. And if it's Gaussian, for example, if it's independent, then the probabilities can be multiplied, right, of the individual probabilities. So then I can write it as n points, or n points of the vector, or n points of the set. Each of them have a Gaussian distribution with their own mean and variance. And then I multiply them to get the joint probability distribution of my data set, right? A common simplifying, the key point here, simplifying assumption in machine learning is when you're encountering a data set, and that's what statisticians do, they say, oh, there is an underlying probability distribution, and this data set is generated by that probability distribution in an IID manner, right? Do you understand what I'm saying when I say this sentence? So there is an underlying probability distribution, and then each data point is IID that is generated by that probability distribution. Like then the joint probability distribution would be then just the multiplication of the individual ones. And if they are the same, then it's the multiplication of the same thing over and over again. You see the problem with that? Statisticians are happy with it, but as a machine learning person wouldn't be that happy about it. Why? Someone. Just make a guess into open as an open. Here you go. That's excellent answer. So why should these things be independent? Right? Even if we assume an underlying probability distribution, why should your data be independent? Data points be independent of each other. Maybe there's an underlying probability distribution, but then that has to be given as a joint probability distribution because of the dependencies between the data points. Usually, real-world data sets are not IID like that. So it's a huge, huge assumption, which makes mathematicians happy, but when you come to the physical world, it doesn't make you that happy anymore. So, but it's a very good assumption. It makes the models go through, and then it provides you an excellent starting point, just like linear systems and nonlinear systems, right? All world systems are nonlinear, but linear systems give you a lot of playground to do a lot of nice things. So it's a bit like that here. IID assumption is like that. All right. So there is a whole literature on how to do sampling and approximations. I haven't gone too much into detail, but I thought it's appropriate to mention at least the Monte Carlo approximation. So that also connects the mathematical world to the real data set world. So let's say, how does Monte Carlo work? Have you done this before, Monte Carlo? No. All right. So the idea is very simple. So we generate S samples from a distribution, and we call them, let's say, x1 to xs. So this distribution could be also uniform. right? Let's say I have between 0 and 100, I generate like 20 points uniformly distributed between 0 and 100, right? That's exactly what I'm talking about. S would be then 20 points. Then, given the samples, we can approximate the distribution using an empirical distribution. So, I say the uniform distribution, but what if it's not uniform, right? So what if I choose another distribution, maybe Gaussian, so say Gaussian. Then the expectation of f of x would be, if I generate them according to any distribution, I can also approximate the distribution of a function of a random variable, approximate the distribution of the function of the random variable, I haven't said it correctly, using the empirical distribution. What that means is I generate the points, then for each point I can calculate f of x, right? I have the function. So what would be the expectation of that, for example? I can take the expectation, it would be then expected value of f of x. In the continuous case, that would be f of x px dx, from the very basics of taking expectation of a function as we were seeing. And then this is approximated by taking the 1 over s, s1 to s, so all the samples, and then I kind of sum them up and then divide to the s. So I can also do this and draw the histogram, right? So like here, so computing the distribution of y equals x squared, right? Where p of x is uniform. So I generate uniform samples between, say, -1 and 1. This is predetermined, given to you. And then it asks, how would the distribution of x squared look like? Of course, you can work out the math in this simple case, but you can also do it numerically using Monte Carlo approximation. This is the analytical result. If you know how to find the distribution of a function of a random variable, you go back to your random probability subject and do this. Or you simply create a lot of points here uniformly, and then for each point you find the x squared, and then you do the distribution. You see, this is the distribution that approximates the analytical result. So that's the whole Monte Carlo approximation idea. And once you have this, of course, you can take the mean, or you can find the variance as such, right? Or you can find the cumulative distribution. So you can do all these things in a numerical way. Of course, it's all an approximation. So the mean will be what we have discussed. Mean, this approximates the expectation. And then this would be the variance, and this would be the probability. Yep. So we got then, they should be actually in this case f of xs, but then that's fine. Good. So again, this is a way of connecting things, but now let's come to the theoretical world. So we need to come to Bayes' decision theory. This is one way to think about, for example, classification. So let's look at two things. So we are given conditional distributions of these two classes. So omega 1 and omega 2. So it's cat versus dog pictures type of, right? So, and then the probability of x belonging to W1 and probability of x belonging to W2, so, or omega 2. I keep switching between them, sorry about that. Probability of a picture being a picture of cat, and probability of a picture x being a picture of a dog, all right, to make it very concrete. And then the a priori probabilities is how many dogs and cat pictures do I have under my hand. Are they equal? Then it's like the probability of having a cat picture is half and dog picture is half. But what if 80% of them are dog pictures and only 20% of them are cat pictures? Then these a priori probabilities would be different, right? Then the classification, binary classification task, looking purely from a probabilistic point of view, will be classify future data. You are given a picture to one of the classes, omega 1 or omega 2. So is that new picture a dog picture or cat picture? And how do I find it? Like in this case, find the regions and the decision boundary, x0, right, to make that decision. In 2 dimensions, in 1 dimension, x is here, it's not 2 dimensions, and 1 dimension, and then I can draw the probabilities. So if the probabilities are like Gaussian, probability of x belonging to omega 1 class and probability x belonging to omega 2 class, right? They overlap, so this is a difficult problem. If it were totally separate, then you find any point in between them, then you have a clean separation, right? But now this means I'm going to make errors no matter what, right? So therefore, I need to know what is the x0 that divides this, separates these regions, and how can I do my best, with some errors, right? Notice that this is the same as finding probability of omega 1 given x and probability of omega 2 given x. Probability of x being a cat picture, probability of x being a dog picture, right? X picture. So these are the a posteriori probabilities. Given x, what is this? These are a priori probabilities. And then these, you see this one and this one. Now, as we discussed just a few minutes ago, the Bayes theorem connects the two. And we have this connection, omega given x and x given omega. Bayesian theorem connects the two. Again, this is just what I said verbally, mathematically expressed, the probability of this greater than that if x is classified to this. So if this probability is higher, then I'm going to naturally classify it to one class, and if the probability is lower, then I'm going to classify it to the other class. That's same as saying I'm going to define these regions, and if it falls here, it belongs to here. If it falls here, it belongs to there, right? In one dimension, things are very simple. There's a nice line and there's a point. Your separating hyperplane is just a point, and everything left to the point is one region, and everything right to the point is the other region for such simple distributions, right? So the decision making is quite straightforward. You can also take into account the a priori probabilities, and then, yeah, that's exactly what's happening here. So if I have the Bayes theorem, you see this probability is related to this probability divided by P of x. But P of x is the probability of the individual pictures. That's given in your training set, or that's given, right? So this is actually a constant. Therefore, it doesn't make any difference, or it's the same for all the classes, right? So when you write this as this, then you get this. Huh? So just combine this with the Bayes theorem, you get this. So what else are given? The probability of classes are given. From your training set, you can deduce them. P of x can be written using the product rule, using again P of x given omega I and then probability of omega I, which are also given. So P of x is also given. And then this Px given omega I is also given. In your training set, you know which pictures are dog pictures and which pictures are cat pictures. Training set is labeled. It's supervised learning, right? We are talking about supervised learning here. So we know the Px given omega I from my training set. What I don't know is, given the other one, which is the left-hand side of the Bayes theorem, I don't know that one. All right? Are you with me now? Have you done this in probability? Probably not. Yes. You have done it. Hey, okay, then that's good. This is just you have done this. This is a good refresher. Oh, Margaret told me she hasn't done inference. Maybe in different subjects. Have you done it in the probability subject here? 954, it was done here. So this was all done.
A little bit, like kind of not directly, but we definitely did very similar things.
Very similar things. Okay, that's good. Then we just refresh. The Bayesian classifier minimizes the classification error probability. So now we need to define the error. We are coming back to minimizing the error, right? In regression, we are minimizing the error with respect to the output. Here we are minimizing, because this is classification, we are minimizing the error with respect to I'm making a misclassification. If I classify a dog picture as cat picture or cat picture as dog picture, then that's an error, and that's what I want to minimize. So the probability, and then I minimize it in terms of the probabilities. Probability of error is if the probability that omega 1, and then given that it's omega 1, I end up in the wrong region. You see, omega 1, given that it's omega 1, probability that x is in the other region. Plus, given that it's omega 2, I end up in R1, which is in the other region. right? So that sum gives me the probability of error. Either I'm misclassifying dog as cat or cat as dog. That's all that is. And then I can write this one, probability of x belonging to R2 given omega 1 as x given omega 1, and then take the integral. This is the capital P, this is the main probability, then this is the PDF, and if I integrate the PDF, I find the probability itself. So this integral is exactly this. I'm just putting it here, this integral is that. And then I can use the bias rule to write it as the reverse, right? So I can write x given this times this as the omega given x times px. Now this error is being in the wrong place here, although I should belong here. This is this shaded region, black shaded region. And this error is the shaded blue error region. So the probability of error is the sum of these error regions. And this gives you kind of a clue on where you should put x0 boundary, right? I intuitively put it to the middle, obviously, because if I shift it, what happens is the total shaded area, blue and black together, which gives you the probability of error, notice that it increases if x0 is shifted to the right or left, because then you get a bigger shaded area. This is the best way to minimize that shaded area. You can also see it visually, solve it visually for this specific simple case, right? Because if you put it here, then all that area will be more shaded, and this, if you put it here, that area will be shaded more, so you'll make a bigger error. So actually we can note that P omega 1 is from the product rule, we can write it over R1 and R2 regions, the total region. We can divide, because they are adding up to the total region and they are not overlapping. I can do this. And this probability of error, then I'm just simply using R2 in terms of R1 and this. So I take this R2 and write it as P omega 1 minus this R1 here. And minus is plus, then I write this which was already there, dx. So this becomes this using this, and I actually write everything in terms of R1, right? And I can do the same thing with R1 and write everything in terms of R2 and P omega 2. So the probability of error wouldn't change. So what you see here is actually then you take the derivative and so on to find but you need to take the derivative with respect to the region. So if we don't do it formally but informally, what you see is I should choose R1 as the region where probability of omega 1 given x is larger than probability of omega 2 given x. So R1 is the region for, let's say R1 is the region for dog, omega 1 is dog. So in that region, probability that a picture of x being a dog should be, of course, be higher than probability of a picture being a cat, because that's the dog region. In the dog region, probability of x being a dog should be higher than the other one. And as I was saying, you can write it in the other way too. So this is constant pre-given. If I want to minimize this, you see the minus sign here, then this should be positive, so I can make it larger. So that means PE is minimized if R1 is the region of space in which P omega 1x is greater than P omega 2x, and R2 is the reverse. But that's very intuitive, so it should be the region, dog region should be the region where probability of x being a dog greater than x being a cat, not the vice versa. So it's very, very intuitively same thing. All right? So yeah, you remembered from previous subject. And not all errors are the same. That's the other thing. So I'm actually here, I assumed that making one error is the same as the other error. And let's generalize this to M classes and risk minimization. Some errors are more costly than other errors. If I mix up things, certain mix-ups are not costly to me from application, some are more costly. Also, I may have more than 2 classes. The digit set, handwritten digits belong to 10 classes, MNIST data set, for example. So if we do that, and assuming non-overlapping region, and these weights determine these costs, we can actually associate the risk for a class, and each class has its own RI region, And then this is just generalizing the previous sum here for 2 regions and only 2 classes. This is the general risk for m classes, each of them having their own lambda weight factor, which wasn't there before, and then this area. Then this is the average risk, is then this probability times Rk. This is also taking into account the a priori probability of the classes happening. And then if I plug it in all together, I get this nice expression that sums it up, double sum. And then the risk is minimized. Again, just we are exactly generalizing the idea before. If in an area, X is in area region Ri, if that risk in that region belonging to that class is less than the risk of belonging to the other class. So in that region, indeed, the picture should belong to that specific digit, not other digits. That risk of belonging to that digit should be higher than, lower than the risk of belonging to the others. So it's a risk minimization. So that's the most general way of, for your reference, putting it. Going back to 2-class case, it's easier to handle. The risk here is then, if I am if it belongs to 1 and I end up with 1, probability of being in class 1 and giving class 1 probability of X, plus if it's 1 and I end up in, if it's 2 and I end up in 1, probability of 2 times, the given 2 being X. So this will be the risk in L1, and then the L2 is written the similar way. Then the decision rule is X belongs to omega 1. We are now making, I'm just going to say the same thing again. If this ratio, if you just make this comparison between 2, and when you rearrange the terms, probability of X given omega 1 divided by probability of X given omega 2 is greater than this right-hand side, will be then the decision rule. And then if it belongs to the other one, if it is less than. So if it's greater than, that ratio is greater than the right-hand side, then you belong to one class, and if it's less, then you belong to the other class. So for 2 classes, we can write it like that. So this ratio of, this probability of X given omega 1 and probability of X given omega 2, this is the likelihood ratio, the very famous likelihood ratio. And the decision test, so if you see this inequality, with if, so this is I'm testing the condition. This rule or test defining the decision regions is known as the likelihood ratio test. So it's very famous. So the whole thing that the likelihood ratio test is doing is I'm minimizing the risk of making an error, and then use that to create a ratio by rearranging the terms and end up with the right-hand side. So it becomes even simpler if the weight of the correct decision is 0. So actually, lambda 1,1 and lambda 2,2 means I'm in class 1 and end up in region 1. I'm in class 2 and end up in region 2. But that's what we want. Therefore, there shouldn't be a cost on it. It can be actually put as 0. That will eliminate those terms, make life a bit easier. And let's say the weight of the errors are equal to 1. So if I make one error or the other error, let's say we give them the equal weight as before, then we have the exact solution as before, actually, because these cancel out, they are 0 out, and then they are 1. So I've got this greater than this, and then if I multiply px given omega 1 times p omega 1 greater than p omega 2 times px given omega 2, right, the likelihood ratio test, you see, this is exactly what I was saying multiple slides ago here, right? So this is the same thing as this simple case where errors, if I'm not making an error, there is no cost. If I'm making an error, I treat the error costs as the equal 1 weight. Then this is the same thing as what's been discussed here. So the whole likelihood ratio test is just creating a likelihood ratio out of this, and then write it as a ratio. So that tells me where do I belong. You see, this is a way of doing classification. Yeah? I mean, in machine learning, we also do a lot of classification. This is a way of good old Bayesian classification. It's a very statistical, probabilistic view of the world. You need to know these probabilities and so on and so on. There is also this Neyman-Pearson criterion. Instead of cost, if you go this path, then error for one of the classes is constrained to be fixed. And then instead of doing this ratio, you do a fixing error and then do some test in another version of making this decision. I'm not going to go there, just mentioning that such a thing exists. And I think in signal processing, if you take advanced signal processing, advanced communication, something like that, you will see the Neyman-Pearson criterion. So this is used in signal processing, so not terribly relevant to machine learning. So all this is a mouthful. Let's do it with an example. I think the example will settle things down, unless you have specific questions first. So you have seen all this stuff in probability subject, really? I was told that this wasn't covered. Sorry?
The more you went into it, the less I recognized.
Yeah, okay. I mean, you must have seen Bayesian theorem. Yeah, I mean, but this is more than Bayesian theorem. We are using the Bayesian theorem to make these classification decisions, decision making, inference. Bayesian inference is the. Okay, well that's good. If you have done it before, maybe it will be easier to. When you see it again, I always feel like that. You see it the second time, third time, fourth time. You always see things in a different way. It happened to me over the years. Like there were things that I haven't seen for a decade. I went back to a decade later. I interpreted everything in a very different way. So in that sense, it's good to see things over and over again. All right, so this is the story. And as I was saying, let's do it the simple Gaussian way. Two-class, one-dimensional problem. PDFs are Gaussian. But you see, they have the same variance, so the distributions are the kind of looking the same, but the means are different, 0 and 1. So this is as simple as it gets, I mean. But it's good to do the simple version. Then there are two classes. So we want to show the threshold minimizing the average risk is equal to this, which looks complicated, but believe me, it is not. And then we assign zero cost to making correct decisions. So if we make a correct decision, there is no cost, which is intuitively meaningful as well. So we want to find the x0. As you can imagine, x0 will be maybe close to the middle, but it may not be, as you can see here. It may deviate from the middle. And why we will see now. I think I will pull the same trick as before and give you a chance to play with it a little bit. And while you're doing that, I can actually start giving you some hints here. And we solve it together. All right? So we have a two-class problem. So actually, let me write a little bit. So you start doing it, right? So give it a shot, right? Go back to the slides, the risks and so on. Risks. That's the So how is it going? Maybe someone will help me. Or do you need 1 more minute? 1 more minute, yep. Yep. Yeah, I wish we had the whole day, but so this whole practice thing is great. I think it works in high school because you pack the kids to the classroom the whole day and then do the classes for the whole day. But yeah, we don't have that much time. So maybe we can start together and then, you know, I'll take over if you haven't finished. So where should I start? What would you recommend? Someone help me? Sorry? Writing the risk. So essentially what we want is, we have written the risk, right? So these are the risks for the first case and the second case. How do I know? The first case is, this is the correct decision, right? And then for the second case, this is the correct decision. And we said there is no cost of making correct decisions, so we zero them out. Then what do we know? We are in X is in omega 1 if L1 is less than or greater than L2? Less than, right? And X is in omega 2 if L1 is greater than L2. Right? So then the boundary is actually L1, L2 boundary is when they are equal. Equal risk will give me the boundary. Right? So if we write it down, if I write actually L1 equals L2, then I end up with the likelihood ratio. Right? So the likelihood ratio will be then P of X given omega 1 divided by P of X given omega 2. You know, I can write it this way as well. Lambda 1, 2, P omega 2, and lambda 2, 1. So it is just, you know, you write them down and then rearrange the terms to create a ratio here. 1, 2, P omega 1. All right? You agree with me on this? Then what do we know? We say that the PDFs are Gaussians. So essentially these PDFs, what are those PDFs? So I can write the Px omega 1. It's a Gaussian, so I write it as, you know, 1 over square root of 2 pi square, right? E to the minus x square, 2 sigma square, right? And the other one is likewise. So you have the this one. You agree with this as well? Yep. E to the now minus x minus 1 square 2 sigma square. They have the same variances. Huh? Okay, I wrote it correctly. But you see, these are already here on the left-hand side, right? In my likelihood ratio, left-hand side of my likelihood ratio, they already appear there, right? So actually, I can write it as, I can write it as Px given this divided by Px given omega 2 belonging to the other class, and I can plug them in. Therefore, we get the constants cancel out, and I get e to the x square over 2 sigma square divided by e to the x minus 1 square 2 sigma square. That would be then exponential, write it like this way, minus 1/2 minus my that becomes it becomes 1/2 1 over sigma square and then 2x minus 1. Yep. You agree? Yeah. So I have this ratio, but I haven't taken the right hand side, right? So I did the left hand side. So this, you see, is this now when I combine with that. But we need to kind of put with that together with the left hand side. So we should do this. So we have this, and then that should come here. And then when we do that, this is equal to the orange part. Right? Okay? So I'm putting equal instead of greater or less than, so that's the boundary. Equal is the middle one. So what are we going to solve for? The question is, what is this x? Right? So we know the right hand side, we know the left hand side. So I need to solve for x. So solve for x, which is the x0, is the boundary Right? In this case, boundary is just a single point. So maybe I should call it x0. So that's the thing I want to solve for. And just rearranging the terms, you can take the log of both sides. When you take the log of both sides and then solve for x0, so take just to give the hint, take log and solve for x0, it gives me the answer. So x0 is 1/2 minus sigma square ln, and then whatever is here, divided by 1/2 p of omega 1. Right? So that's basically it. Notice, if the costs are the same and a priori probability of two classes are also the same, then I get half, the middle. But that's intuitively the case. If it's not the same, if the probability of having more, if we have a probability of having more dog pictures, for example, even if the lambdas are the same, then you will get the plus log here. It will shift the boundary to the left. But if you have more cat pictures, then inside the log will be less than 1. Then you get a negative. Then negative will plus, and it will shift the x0 to the right-hand side. And how much you shift depends on the variance. So this whole thing makes a lot of sense when you interpret the equation. Every term kind of gives you some idea. But in the equal priors, if equal priors and costs, right, then x0 equals 1/2. But that's as expected, right? So that's what's shown on the picture. But a priors may be different. Yeah, I think this summarizes the whole story and likelihood ratio, and essentially all I am saying is I should have the region defined in such a way that in that region the probability of the picture belonging to that class should be higher. Therefore, the risk of that associated risk of making an error in that region should be the smallest. So that's the moral of the whole story. So now actually this is an important slide. Why? Because until now we've been doing nice statistics and probability theory, right? How do you do it with the real life? I mean, this machine learning subject is a bit, I tried to make it as much real life as possible. How do I find these things? So actually the good thing is we can actually calculate a lot of the stuff from a given data set. So until now, what did we assume? We assumed that conditional distributions are given, and we assumed that the a priori probabilities are given. Beforehand, I said the probability of having class 1 is this, probability of having class 2 is this. How do you estimate them from a real data set? And that's quite easy. If you are given a data set with x's and their labels, right? The w's, omegas are the classes. These can be directly estimated from the data using Monte Carlo methods. Just like we discussed before, and using the Bayesian theorem, you can estimate these. Because you actually in the data set, you can say, given an x, probability of x belonging to one of the classes, with using all of the x, you can actually estimate that. So therefore, you can also estimate these using the methods we discussed. And these a priori probabilities, you can also estimate. So let's say n1 and n2 are the cardinalities of the data with labels omega 1 and omega 2. That means, let's say you have 100 pictures in your training set, and 50 of them are dog pictures, 50 of them are cat pictures. That means 50 over 100 is your probability of having omega 1 cat pictures, and 50 over 100 is the probability of a priori probability of having dog pictures. But if your set is 100 and there are 20 dog pictures and 80 cat pictures, then a priori probability of having dog pictures, p omega 1, is just 20 over 100 and the other one is 8 over 100, right? And then you are supposed to plug them into your likelihood ratio from the data set. These are, of course, estimates, but that's the best you can do with the data set, the estimation. And the same thing with the other ones that we have discussed. Probability of x belonging to this and x that. So there are better methods for such estimation problems, but we will come to that a bit later, right? So the last word in inference and decision in classification, I think this slide is worth mentioning. Otherwise, I wouldn't have put it, I guess. We can, I could think, maybe that's my interpretation, I could think three main approaches to decision classification problems. So, first first class is called the generative models. So the idea here is, first you determine Px given C for each class individually, and that's a generative model. If you can probability of x given C, that means I can actually generate, given a class, I can generate x's, right? So that's a generative model. And then using Bayes to determine what is the probability of this x belongs to a certain class. For example, for a new x, once you have the x given C, right, then I can use Bayes' theorem to find probability of C given x. Given x, given the picture, what is this, a dog picture or cat picture? That would be what's the probability of this picture being a dog picture or cat picture? That's the probability of which class does it belong to, right? If you have this predetermined in your model, then you can use Bayes' theorem to calculate the other one. So determining this first gives you also a chance to do a generative model, because one can generate synthetic data points in the input space. So that's the generative model. The other model, the other approach is determining PC given x directly. These are called discriminative models. So you don't bother spending time trying to figure out what is Px given C. You just go for PC given x. You still use probability, but then in both cases, the PC given x allows us to assign new x to classes. That's exactly what I'm talking about. New x comes, you say, this picture is a dog picture, this picture is a cat picture, right? The first two are inherently probabilistic. So you do this probability stuff. There is a non-probabilistic approach too. Some people think all of the machine learning is statistical probabilistic. I disagree with that. You can actually happily do classification without doing any probability distribution or any assumptions about an underlying joint probability distribution, right? Leave AID aside, you don't even have to decide a joint probability distribution either. Just find a function which is called the discriminant function, and which maps the input x to a given class label. How do you do that? That's exactly what we have been discussing in the beginning, hyperplanes, right? Hyperplane, you take the space of x, put a dividing function, linear or nonlinear, left side is this, right side is that. All right, that's simple as that. Is there any probability here? No. You draw a line. You draw a hyperspace. Hyperplane. Yes, thank you. Thanks for that. You draw a hyperplane. Or you draw a function. Actually, in general, it's just a function. It's an n-dimensional, n-1 dimensional function. Because if the space is n-dimensional, then your function should be n-1 dimensional. If it was 1-dimensional, then you look for a point which is 0-dimensional. That's what we did. If it's 2-dimensional, then you look for a line or 1-dimensional curve. If it's 3-dimensional, you look for a plane or 2-dimensional surface that divides your 3-dimensional space, and so goes on. So what you want is a n-1 dimensional hypersurface to divide your space into 2, 3. If it's M class, then you need, of course, divided to n, right? So this is kind of also important to see. So the first two, though, are what we have been just discussing. And I guess I ran out of time, right? Very much so. So we will continue after the mid-semester test. And then we go to unsupervised learning, then supervised learning, as I was saying, fun stuff. Good luck tomorrow. I'll be there, of course, the whole time to answer any questions. Right? And remember, it's in a different place. Check the LMS for location and everything. Yep. Thank you. See you tomorrow.